So now that we have seen in an earlier video the simple RNN kind of architecture, and we went through a simple example of time series prediction, I think it's worthwhile trying to understand what are the performance limitations of RNN, of simple RNN architectures, and that is going to motivate us to developing a slightly more advanced or considerably more advanced kind of architecture out of this kind of discussion. So the question that I think it's worthwhile kind of trying to answer is the following. Can simple RNNs capture long-term time dependencies and the approach that we'll actually follow here is we will unroll the simple RNN architecture, and it's assuming, let's say, a classification kind of use case, and look at how the network kind of learns by looking at the gradient flow during the training kind of procedure. So this will actually reveal to us how the limitation of, as we will see, the answer is a negative answer, but we need to have the block diagram in order for us to sort of capture that limitation in our minds. So what I'm going to do here is I'm going to draw this kind of architecture. So we have some gates that are associated with the matrix W as we have seen it, multiplying a hidden state ht minus 2, which is itself is coming in from the previous unrolling instance. Then we have a bias addition, and of course we receive the input, which is itself, as we discussed earlier, multiplied by a matrix U. So this is my input ht minus 1. Then this will give us some form of an activation ht minus 1. We'll pass that through that tan H nonlinear unit to obtain an ht minus 1. And we will also then take the hidden state. I just have only one layer at this moment. It doesn't really matter for that discussion to have one or more. We're going to have a tensor V, which is feeding this gate V ht minus 1. We have the C, the bias. And then, as we discussed, we're going to assume some form of a classification example. So we need a softmax to produce my y hat of t minus 1. And then we have evidently a cross entropy loss to obtain an LT minus 1 at the top. And this cross entropy loss is requiring the ground truth YT minus 1. In general, these two will be vectors. So I went ahead and actually drew another instance of this next to it. And this previous instance was giving it LT minus 1, the T minus 1 instance. This is the T instance. At this moment in time, the network is here. And evidently, there's going to be this very, very important line that connects these two. And for those who do not see it, then that's basically this line which I just drew over here. So that is really the, so what important kind of connection between the two instances. The hidden state is carrying forward in order to create this dependency with the previous hidden state to the output h of t, as we discussed. Okay, so let's see what happens now during backpropagation. And we've seen backpropagation, the first principles of backpropagation in another video for those who have missed it, but backpropagation, as we discussed, will actually involve some form of local gradient calculations, upstream and downstream gradient calculations involving local gradients at each kind of gate. So we see the gradient that is floating from the, let's say, the loss function, going through this whole sequence of gates. And this sequence of gates have nothing different than the sequence of gates we have seen in fully connected layers, because that's really a fully connected layer followed by cross entropy and softmax. And we already know how to backpropagate fully connected layers. And arrives over here. So this is my DHT minus 1. I'm following the notation that we have introduced earlier, where we proceed with D, the derivative, D for derivative, the gradient that we see here. Okay, so this is so this gradient will actually flow over the tan H, will actually go into this kind of adder, and it will be broken down into the parts which are needed for us to sort of calculate exactly how they, actually I forgot to draw the tensors U. Okay, so then it will arrive over there, here, this gate, which is really very essential, and it will go over there and go backwards. And this is the reason why this process is called in the literature backpropagation through time. So it will reach this point, and if you followed along in this kind of that other video on the introduction of backpropagation, it sees this kind of a hidden gate, or there's a hidden gate over here that effectively this is the copy gate or the fork gate, whatever we call it back then, and it will definitely receive this gate also another gradient coming that it is called DHT. DHT minus 1. I kind of made a mistake here. This is DHT because the tensor is HT. This will be the DHT minus 1. And so this DHT minus 1 and the other version of this DHT minus 1, the other component of DHT minus 1 will be summed over to form this kind of gradient. That was the effect of that copy gate, and the whole process will repeat itself, and will go back in time, and another stage back in time. And as we have seen in backpropagation discussion, there are two possibilities that actually can happen. Typically, the gradient kind of, as it goes through the grade, is adjusted, as we had also formed this kind of analogy of a water valve. And there are two possibilities that are going to happen, and these possibilities depend on matrix W. So let me write this down. The matrix W, you can show that the matrix W is responsible for the diminishing or explosive nature of DHT, which is by definition the partial derivative of, let's say, of the loss with respect to HT. And you can actually see that and show, the proof is kind of outside of this discussion, but the structure of this matrix W, and it all depends because it is actually being involved in this backpropagation process. If I can say that if the eigenvalues of W are less than 1, then effectively we have a diminishing situation. So gradient flow diminishes means lots of problems in terms of training, because there is, effectively the adjustment of parameters effectively stops. And you can think about that when you consider the stochastic gradient descent kind of equation that depends on that kind of gradient, on how the parameters are adjusted. So, and on the other hand also, this is A, this is B, if the eigenvalues of W are larger than 1, then we have an explosion of the gradient. And this is a very problematic situation too, but we can actually clip the gradient, and we can do certain tricks to adjust, if you like, that explosion and manage it. But the diminishing nature is kind of very problematic, because effectively training stops. And so the gradient typically is not, empirically has been shown that is not able to survive for more than a few of these instances back in time. And we also are going to introduce another capability in the backpropagation through time. We're going to have a window over which we are backpropagating. Evidently, for applications that require many steps, we are going to the process of backpropagation is going to be very long. So, and coupled with the fact that the gradient may not even survive for long periods of time, what we decided to do is we decided to use a kind of a truncation window of, let's say, 20, or whatever the number is, 10. It's a hyperparameter. And at every truncation window, we are resetting the backpropagation process, and we are starting from scratch with respect to this kind of gradient calculation. So when you hear people saying that RNNs, provide some form of memory, then this is the memory. This is this connection between the two instances, and how much gradient flow you can pass back in time heavily determines how much you can remember. And apparently, empirical observations of the RNNs indicate that it cannot really remember. The simple RNNs cannot really remember for long periods of time. So we need to move on into another architecture. Like you probably guessed, somehow this controlling of this W matrix has to be there built into that kind of architecture. And we will call this architecture long short-term memory architecture. And for those who want to just remember a simple example to demonstrate this kind of exploding and vanishing kind of gradients, and without having to involve yourselves into decomposition of matrix decomposition and eigenvalues and so on, I have provided here a simple block diagram of what is effectively called infinite impulse response filter, but it's kind of not necessarily need to remember that. Where you will receive some kind of input x of t, and you are adding from some scaled version of what you remember in the previous instance of that kind of output of that device, h of t. So the equation kind of matches what you have seen earlier. There's no nonlinearity here, but the equation kind of matches what we have seen earlier as the, trivialized equation of an RNN, where we have some dependence on the previous state and of course the input. And so if you see what's happening, and if you just do the calculations for, let's say, W being the absolute value of W being less than 1, then you can actually see for some impulse that we send at the input delta t, then we can see exactly how the hidden state kind of varies over time. And it's the envelope of this hidden state means the absolute value of the hidden state is going to diminish. So in fact, with some kind of exponential way. And evidently, when the W is becoming larger than 1, then that hidden state is going to explode. And this is definitely an analogy that we can always use to remember what is happening inside the sort of a simple RNN.